So the rules for differential calculus then. First step is to write down this table of differentials to refer to. Just one or two notes on this table. On the left-hand side of this table is the function, f function, that we're going to differentiate. And the most obvious, the most general function is this one, ax to the n. X is the variable, and the some constant may be in front of it, like 4 in this example, and the x might be raised to a power n. So 4x cubed is an example of that first type of function. So a general function, ax to the n. The differential turns out all you do is bring the power down, n, and multiply it by the number in front, and then take 1 off the power, n minus 1. So this example, 4x cubed, I multiply the 4 by the 3 to get 12, and then take 1 off 3 to get 2, and to 12x squared. So you can write down the answer. It's as easy as that. So we looked at the first one. This general rule is the one that we apply most often, because most functions have this sort of form. Some number in front of the variable x. So 4x cubed would be a good example. All you do for the general rule is multiply the number in front by the power, 4 3 to 12, which is this here, and then take 1 off the power, 12x squared. Done. Okay? The variable doesn't need to be x. It could be t, and that's often the case, t for time. So 4t cubed would be differentiated to give 12t squared. So we need to know what the variable is, and the general case is x. The convention, we've looked at this sort of already. So this is a useful convention because it tells me I'm differentiating. So this one here, dy by dx, tells me I'm finding the differential of y with respect to x. So if I had y equals ax to the n, I differentiate it to give an x to the n minus 1. If I had y equals sine ax, to differentiate it, I have dy by dx. Okay, that's the convention. So if the variable was not x, it was t, I'd write dy by dt. And if this wasn't y equals, it was volume equals, like we were just saying, it would be dv by dt. So these change depending on what symbols I'm using for the variables in the function. Okay. Another convention for the differential is this, and this goes along with this actually. If I'm using this convention to write the function fx, and this is a useful convention because it tells you immediately what the variable is, x, then the shorthand way of writing the differential is just f prime. So f prime x means the differential of that function. But the rule's the same. Okay, so the rules are the same, just two conventions to write the differential. Now let's look at the second function, please. Second function, y equals sine ax. When I differentiate that, whatever number is inside here as well as the variable x, that number comes out and goes in front, and the sign changes to a cosine. How these rules are arrived at, the first one, the second one, and all the others, can be derived from first principles. And in the book, it goes through calculus from first principles to arrive at these rules. But once you've done that, there's no need to go through the first principles every time. You just use the rules. So we're not going to worry too much about deriving from first principles. We're just going to use the rules. Enough to say on that, though, that if we go back to this example here, if I want to find the gradient at this point, for example, what I'd do was, and we did this at autograph, is put a little triangle in and find the gradient, okay, y divided by x. But if I want to know what the gradient is at this point, I could do with a small triangle, and the smaller the triangle is, the closer I get to the value of the gradient at that point. Especially as it's a curve, if I take a triangle here, I'm averaging it over the curve. It's not a straight line. And what calculus does is investigates what happens as the triangle gets smaller and smaller and smaller until it disappears effectively. And that's the idea of calculus from first principles. But let's not go down that route. Enough to say that if we do that process, we end up with these rules. And it turns out that the differential of a sine function is the cosine function. So an example might be 3 sine 2x. So if I differentiate that, the 2 comes out, multiplies by any number that's in front. So 2 times 3 is 6. And the sign changes to a cosine. And inside, the 2x stays the same, 2x, 2x. So once you know the rule, it's easy to apply. Look at the next one. Cosine changes to sine. That's from first principles. That's what the rule tells us, except for this negative sign. So if I differentiate a cosine function, that turns into a sine, but there's a negative in front. So again, look at the example. 2 cos 4x. The 4 comes out and multiplies by the 2. 8. But it's negative. So minus 8 sine 4x. Look at the next one. This function is the exponential function, is one that we've come across before. And I might have mentioned at the time that the exponential function is the only one that's its own differential. If I were to plot a graph of the exponential function, and let me just quickly do that at the end here, it would look a bit like this. And if I look at the curve, actually it's going to disappear, so let's do it like that. Okay. If I look at this curve, this is the only function, if I plot e to the x, where if I want to know what's the gradient of this function at that point, I just look across and there it is. The value of the function tells me the gradient. What's the gradient at this point? It's that. So this is the only function where the gradient is the value of the function at a point. If I go back to the rule then, that's what this is saying effectively, except for the fact that if there's some constant in there as well, then that a comes down and goes in front. But apart from that, look, the function doesn't change. E to the ax stays as e to the ax. So 3e to the 2x, I'll bring the 2 down, times that by the 3 to get 6, and then the rest stays the same. The rule would apply if it was negative or if it was a fraction. Okay? It applies to any number. Looking at the next 2, these are special cases actually of the top one, so but worth writing down. Ax, if there's no power to the x, it means to the power 1. So if I bring the 1 down and multiply it by the number in front, 4 times 1 is 4, and then I take 1 off the power, 1 take away nothing is nothing, and anything to the power 0 is just 1. So effectively the x disappears and I'm left with just a constant. So that's a special case. If I'm differentiating ax, I'm just left with a number. So 4x becomes 4, 3x becomes 3, and so on. Okay? A constant, when I differentiate it, it's 0. It might be worth just looking at these 2 again underneath. If I plotted a graph of y equals 3x, what might I expect to see? Straight line, what, horizontal? Not quite, because as x increases, this number's going to get bigger, isn't it? So it will be a straight line, but it'll be like that. The gradient of this line will be a constant, just 3. And remember, the differential tells us the gradient, so it's not surprising that the differential of 3x is 3. Okay? If I plotted a graph of y equals 4, what would it look like? A horizontal straight line going through 4. It doesn't matter what x is, y is 4. Somebody else, what's the gradient of that line? 0. Horizontal. So That's where these rules come in, look. The differential of a constant is 0. It doesn't matter what that constant is, the gradient is 0. And that's what that rule is telling me there. And lastly, there's another one that we come across, a natural log function as we go along with this maths. And so that's a special, another function. There are others, but these two, this one in particular, I thought I'd put in. The natural log function, any constant inside it actually just disappears and it becomes 1 over x. So the natural log of 3x or 2x is just 1 over x. But if there's a number in front, like 3 log 2x, then it becomes 3 over x. So the 3 stays on top. Okay? So that's the table of differentials. And if you've got that to hand and you're asked to differentiate a function, you use the table to do it.